Black holes are among the most extreme objects ever conceived by science. They are regions where gravity becomes so powerful that nothing, not even light, can escape. Inside them, the familiar rules of physics collapse, and the fabric of space and time folds in on itself. For decades, astronomers believed they understood how black holes were born and how they grow. Small ones form when massive stars die. Over billions of years, those black holes merge, feeding on gas and dust until they become the colossal engines that anchor galaxies. But recent discoveries have revealed a puzzle at the edge of the observable universe. Using the sharp eyes of the James Webb Space Telescope, scientists have found supermassive black holes that existed when the universe was less than 1 billion years old. They are enormous, millions, even billions, of times more massive than our Sun, and they appear far too soon in cosmic history. According to the physics we know, these black holes shouldn't exist. Their discovery has forced scientists to re-examine the very timeline of cosmic evolution. How could something so massive form so fast? And what do these ancient monsters tell us about the early universe itself? This is the story of the black hole that shouldn't exist, a journey to the dawn of time, where the universe challenges everything we thought we understood. To understand why these early black holes are so mysterious, we first need to understand what a black hole is. A black hole forms when matter is compressed into a volume so small that its gravity becomes irresistible. The boundary surrounding it is called the event horizon, a point of no return. Anything crossing this boundary, whether gas, dust, or even light itself, is lost to the universe beyond. At the center lies the singularity, a region where density and curvature become infinite. In this place, our equations of space and time break down. Einstein's general theory of relativity predicted that such objects could exist, but for decades they remained only mathematical curiosities. Astronomers now classify black holes by size. Stellar black holes form from the collapse of massive stars, typically 10 to 20 times the mass of the Sun. They scatter throughout the galaxy, invisible except for the radiation from matter falling toward them. Intermediate mass black holes between 100 and 100,000 solar masses are rarer and harder to detect. They may bridge the gap between stellar and supermassive types. And then there are supermassive black holes, giants millions or billions of times heavier than the Sun. Nearly every large galaxy, including our Milky Way, contains one at its core. Ours is called Sagittarius A, a calm, supermassive black hole about 4 million solar masses in size, located 26,000 light-years away. Black holes cannot be seen directly. Instead, astronomers study their influence, the motion of nearby stars, the swirl of glowing gas in accretion disks, and powerful jets of particles streaming at near-light speed. These indirect signatures allow scientists to measure their mass and understand how they shape galaxies. For most of the 20th century, black holes seem to fit neatly within our models of how the universe evolves. Then, telescopes began looking back in time across billions of light-years and saw something that no model could explain. For decades, astronomers believed they understood how black holes formed. The story begins with stars, massive, brilliant spheres of gas that live fast and die violently. A star spends most of its life balancing two powerful forces. Its core produces energy through nuclear fusion, pushing outward, while gravity pulls inward, trying to crush it. When a star, many times heavier than our Sun, exhausts its fuel, that balance fails. The outer layers collapse inward, triggering a supernova explosion, one of the most energetic events in the universe. What remains after the explosion depends on the star's mass. If it's heavy enough, gravity wins completely. The core collapses into a black hole, a region so dense that even light cannot escape. These are stellar mass black holes, the first step in a hierarchy of cosmic giants. Over time, these smaller black holes can grow. They merge with other black holes or feed on gas and dust in their surroundings. Each merger releases gravitational waves, ripples in the fabric of space-time first detected in 2015 by LIGO. Through countless such events, a black hole can increase its mass thousands of times. In the centers of galaxies, the process is even more dramatic. As young galaxies form, clouds of gas spiral inward under gravity's pull, feeding central black holes. Over billions of years, these objects become supermassive black holes, millions or billions of times the mass of the Sun. Their immense gravity affects everything around them. They shape how stars are born, how galaxies evolve, and how energy moves through the cosmos. In theory, it takes time, billions of years of cosmic evolution, for black holes to reach these incredible sizes, and that until recently made perfect sense. But when astronomers looked back to the universe's earliest epochs, they found something that broke this timeline. Just 500 million years after the Big Bang, an instant in cosmic terms, supermassive black holes already existed. They were fully grown, bright and active, when the universe itself was still in its infancy. This discovery didn't just challenge a few equations, it threatened to rewrite our entire understanding of cosmic evolution. In the next chapter, we'll travel to the edge of the observable universe, where the James Webb Space Telescope captured light that began its journey nearly 13 billion years ago. There, hidden among the first galaxies, scientists found the black holes that shouldn't exist. In December 2021, a rocket carrying humanity's most advanced observatory launched into the quiet of deep space. The James Webb Space Telescope, a collaboration between NASA, ESA, and the Canadian Space Agency, was designed to look further back in time than any telescope before it. Unlike Hubble, which observes mainly invisible and ultraviolet light, Webb sees in infrared light stretched by the expansion of the universe over billions of years. Infrared vision allows Webb to pierce through cosmic dust and reveal the faint glow of the very first galaxies. When Webb's instruments came online in mid-2022, astronomers began scanning deep fields, tiny patches of sky filled with galaxies so distant that their light began its journey more than 13 billion years ago. What it saw astonished them. Among the first images were bright, compact objects known as quasars, powered by supermassive black holes. These quasars weren't just old, they were ancient. They existed when the universe was less than 1 billion years old, during an era called the Cosmic Dawn. One of them, found in a region known as Sears 1019, appeared to host a black hole roughly 10 million times the mass of the Sun. Another, in the galaxy J20+0641, was nearly 2 billion solar masses, already as massive as the black holes at the centers of mature galaxies like our own. According to our best models, there simply hadn't been enough time for gravity to build such giants. Even if these black holes had been growing at the fastest possible rate, what physicists call the Eddington limit, they shouldn't have reached this size so soon after the Big Bang. The data forced astronomers to confront a fundamental question. If supermassive black holes existed in the universe's first billion years, how did they form so quickly? Some suspected Webb's instruments might be mistaken, that perhaps these weren't black holes at all but starburst galaxies glowing with new stellar activity. But spectroscopy, Webb's ability to separate light into its chemical fingerprints, confirmed the truth. The spectra revealed signatures of fast-moving gas, heated by a central, compact source of immense energy. There was no doubt these were black holes, and they were real. With each new image, the mystery deepened. Instead of finding the gradual buildup of galaxies and black holes that theory predicted, Webb was revealing a universe that seemed to have raced ahead of schedule. Massive structures appeared where none should yet exist. In the first billion years of cosmic history, something extraordinary was happening, something our models don't yet capture. The discovery of these ancient black holes marked a turning point in cosmology. It wasn't just a new observation, it was a challenge to our understanding of how the universe itself grows and evolves. The universe is 13.8 billion years old. When the James Webb Space Telescope looks back to the first billion years, it's seeing a time when the cosmos was young, still forming its first galaxies, its first stars, and its first black holes. But Webb's images revealed a mystery. Supermassive black holes, already millions or billions of times the mass of the Sun, existed when the universe itself was barely out of its infancy. How could they have grown so fast? That question lies at the heart of what scientists now call the growth paradox. To reach supermassive size, a black hole must consume matter. It feeds on gas, dust, and stars that wander too close. But there's a natural limit to how quickly this can happen. As matter falls inward, it heats up and emits powerful radiation. That radiation pushes outward, counteracting the pull of gravity. This delicate balance, the point where a black hole can grow no faster, is called the Eddington limit. At this rate, a typical black hole might double its mass every 50 million years. Even if one began as a massive stellar remnant, it would take billions of years to reach the size of the monsters Webb observed. Yet somehow these ancient black holes achieved it in less than 1 billion years. One explanation is that they started out much larger than we thought. Instead of forming from collapsing stars, perhaps the very first black holes were born directly from enormous clouds of gas, what scientists call direct collapse black holes. These cosmic seeds could begin their lives with masses of 100,000 to 1 million suns, giving them a huge head start. But that theory has its challenges. For a gas cloud to collapse directly into a black hole, it must avoid fragmenting into smaller stars along the way. That requires special conditions. Regions with low metallicity, little turbulence, and intense ultraviolet radiation to keep the gas warm. Such environments might have existed only rarely in the early universe. Another idea suggests that the first generation of stars, called population 3 stars, were much more massive than any star we see today. These primordial giants could reach hundreds of times the mass of the Sun before collapsing. When they died, they may have left behind the earliest black holes, which then merged rapidly to form larger ones. But even this explanation struggles to account for the extreme masses Webb has revealed. The mergers would need to happen at extraordinary speeds, and the feeding would need to continue almost without interruption. A more radical hypothesis challenges the very physics that limits black hole growth. Perhaps in the dense, chaotic environment of the early universe, radiation pressure didn't restrict accretion in the same way it does today. If the flow of gas was thick enough or chaotic enough, black holes could feed faster than the Eddington limit allows, a process called super-Eddington accretion. If true, it would mean the laws we observe locally might not apply universally, at least not in those first billion years. Each of these possibilities paints a different picture of the universe's youth. Either the first black holes were born far larger than we ever imagined, or they grew in ways that defy our understanding of physics. Both scenarios challenge decades of theory about how structure forms and evolves. The growth paradox isn't just a question of numbers, it's a question of history. If black holes grew too fast, they may have influenced the birth of galaxies themselves. They could have triggered early star formation, shaped the first cosmic winds, and set the stage for how the modern universe looks today. What began as a simple observation, a few bright points of light in Webb's deep fields, has become one of cosmology's most profound challenges. Every black hole found in those early epochs deepens the paradox, reminding us that the universe's first billion years remain a mystery still unfolding. The James Webb Space Telescope revealed a universe filled with contradictions. In its infrared vision, astronomers see galaxies that are too massive, too structured, and too bright for their age. At their centers sit black holes that by all logic shouldn't exist, cosmic giants that seem to have skipped the slow process of growth altogether. Scientists now face one of the most intriguing questions in modern cosmology. How do you build something this massive, this early, in a universe that's barely begun? To solve this puzzle, researchers are exploring several competing theories, each offering a glimpse into a universe far stranger than we once imagined. The first possibility is bold and simple. Perhaps these early black holes didn't start small. Instead of forming from collapsing stars, they were born directly from enormous clouds of primordial gas, a process known as direct collapse. In this model, regions of the early universe contained vast reservoirs of hydrogen and helium untouched by heavier elements. Under the right conditions, low turbulence, high temperature, and strong ultraviolet radiation, these clouds might have avoided fragmenting into smaller stars. Instead, gravity would have pulled the entire cloud inward at once, forming a black hole seed hundreds of thousands of times the mass of the Sun. Such a massive seed could easily grow into a supermassive black hole within the universe's first billion years. But the evidence for this process remains elusive. Astronomers have identified a few potential candidates, bright, compact sources that could be the aftermath of direct collapse, yet none have been confirmed beyond doubt. Still, the theory remains one of the most promising explanations for the enormous black holes seen by Webb. Another theory looks to the universe's very first stars, the mysterious population 3 stars. These were the pioneers of starlight, formed from the raw materials of the Big Bang, hydrogen, helium, and almost nothing else. Without heavy elements to cool their gas, these stars could grow to extreme sizes, hundreds, perhaps thousands of times the mass of our Sun. When they reached the end of their short, brilliant lives, many would have collapsed directly into black holes. Each one could serve as a seed, merging with others or accreting gas to become larger. Over hundreds of millions of years, such mergers could give rise to the supermassive black holes seen in the early universe. The challenge? We have never seen a population 3 star directly. Their light would have long since faded, and their remnants are difficult to distinguish from younger, metal-rich stars. Webb's deep field surveys, however, may soon detect their fingerprints, faint chemical traces hidden in the oldest galaxies. If they do, it could confirm that the first generation of stars helped create the universe's earliest black holes. Another possibility bends the rules of physics, at least as we understand them today. In the dense, turbulent environments of the early universe, the balance between radiation pressure and gravity may have behaved differently. If gas poured toward a black hole faster than radiation could push it away, growth could occur at super-Eddington rates, far exceeding the theoretical limit. In this model, even small black hole seeds could grow incredibly quickly. Instead of billions of years, it might take only a few hundred million to reach the masses Webb observes. Astronomers are testing this idea by studying quasars, luminous beacons powered by actively feeding black holes. Their brightness and variability reveal how efficiently matter falls in and how fast a black hole can grow. If Webb and future observatories find signs of sustained super-Eddington feeding, it would reshape our understanding of how the first cosmic giants came to be. Some scientists have proposed a more radical idea, one that traces black holes back to the moment of creation itself. According to this theory, primordial black holes may have formed just fractions of a second after the Big Bang. Quantum fluctuations in the dense, rapidly expanding early universe could have created regions where matter clumped together so tightly that they collapsed immediately into black holes. If even a few of these primordial black holes survived, they might have served as seeds for later supermassive growth. This theory could also help explain part of the mysterious dark matter that seems to make up most of the universe's mass. So far, no direct evidence confirms their existence, but ongoing studies of gravitational lensing and cosmic background radiation continue to search for clues. If primordial black holes are ever found, they could rewrite the story of how the universe began. Each of these theories tries to solve the same paradox: the universe's first black holes grew too quickly. But perhaps the paradox lies not in the black holes, but in our understanding of the universe itself. Some cosmologists have begun exploring the idea that the early universe may have evolved differently than our models suggest. If cosmic expansion, matter density, or even the laws of gravity behave differently during those first billion years, it could explain why massive black holes appeared so soon. Alternative theories of gravity, variable dark energy, or interactions between dark matter and radiation might all play a role. These ideas remain speculative, but they highlight an important truth. Every observation Webb sends back challenges us to question what we think we know about reality. The search for answers continues in observatories around the world, in the data flowing from space telescopes and in the simulations running on supercomputers. Each model offers part of the picture. Each new discovery reshapes it. The universe may be 13.8 billion years old, but our understanding of its origins is still in its infancy. The black holes that shouldn't exist are not just astronomical curiosities. They are windows into the earliest moments of creation, reminders that even the oldest parts of the cosmos can still surprise us. In the next chapter, we explore how these ancient black holes may have shaped the first galaxies, and how, in turn, those galaxies shaped everything that followed. Galaxies are the grand structures of the universe, vast collections of stars, gas, dust, and dark matter bound together by gravity. For much of cosmic history, they have served as the homes of stars, the engines of creation, and the stage upon which the universe's story unfolds. At their centers lies a paradox. Almost every large galaxy we observe, and one piece including our own Milky Way, harbors a supermassive black hole at its heart. These black holes and their host galaxies appear to have grown together, influencing each other in a delicate cosmic balance. But Webb's discoveries of massive black holes in the early universe raise a profound question. Which came first, the galaxy or the black hole? For decades, astronomers assumed that galaxies formed first. Gas cooled and condensed into stars, creating the gravitational well that would eventually allow a central black hole to emerge and grow. But the early universe, seen by Webb, tells a different story. In some of the youngest galaxies ever observed, black holes already appear fully grown. They are not passengers within their galaxies. They are the drivers, shaping their surroundings even as the first generations of stars ignite. This discovery has led to a new way of thinking about cosmic evolution. One where black holes and galaxies form together, locked in a mutual relationship that defines their growth from the very beginning. When a black hole feeds, it releases enormous amounts of energy. Matter falling toward it forms a swirling accretion disk, heated to millions of degrees. Some of that energy escapes in the form of high-speed jets, streams of particles traveling near the speed of light. These outflows can stretch for thousands of light years, shaping their galaxies in ways both creative and destructive. The process is called feedback. Too much feeding, and the black hole's energy can blow away the gas a galaxy needs to form new stars. Too little, and the galaxy may collapse inward under its own gravity. In this way, the black hole acts as a regulator, a cosmic thermostat maintaining the balance between creation and destruction. This balance may have existed even in the first billion years. Some of the earliest galaxies Webb has observed appear surprisingly mature, massive, dusty, and rich in heavy elements. These are signs of rapid evolution, suggesting that black holes played an active role in shaping them from the start. One striking example is the quasar J0313-1806, powered by a black hole over 1 billion times the mass of the Sun, yet seen when the universe was only 670 million years old. The galaxy surrounding it already shows evidence of strong winds, likely driven by the black hole's intense energy. Even at this young age, the relationship between galaxy and black hole seems fully formed. Astronomers call this process co-evolution, the idea that galaxies and their central black holes grow hand in hand. As the galaxy feeds its black hole with infalling gas, the black hole in turn shapes how the galaxy grows. Together, they build the large-scale structures we see today. Observations of nearby galaxies show a clear connection between the mass of a galaxy's central black hole and the mass of its surrounding stars, a relationship known as the M-sigma relation. This link suggests that whatever governs galaxy formation also controls black hole growth. Webb's findings now push that relationship back to the universe's earliest days, revealing that the pattern was already in place from the start. But the story isn't simple. Some early galaxies appear to host black holes that are too massive for their size, breaking the expected relationship entirely. If true, it could mean that in the beginning black holes grew faster than their galaxies, forcing the cosmos to catch up later. Others may show the opposite, galaxies that matured first, with black holes that lagged behind. This diversity hints that multiple paths may lead to the cosmic systems we see today. Black holes don't just influence their host galaxies, their outflows can travel far beyond, enriching intergalactic space with heavy elements and altering how neighboring galaxies form. In this way, the first black holes may have helped shape the cosmic web, the vast network of matter that defines the large-scale structure of the universe. Even our own Milky Way bears the marks of this cosmic heritage. At its center lies Sagittarius A, a black hole 4 million times more massive than the Sun. Though quiet today, evidence suggests it was once active, shining as a quasar billions of years ago when the Milky Way itself was still forming. The same processes that sculpted those early galaxies may have set the stage for our own. Each new observation from Webb adds another piece to this intricate puzzle. Galaxies and black holes appear to be partners in creation, each shaping the other, each revealing the story of the universe's first light. The ancient black holes once thought impossible may, in fact, be the architects of everything we see today. In the next chapter, we'll explore how scientists are piecing this story together. Through massive computer simulations, multi-wavelength observations, and the next generation of telescopes designed to uncover what even Webb cannot see. The quest to understand the black holes that shouldn't exist is far from over. In many ways, it's only just begun. The story of the black holes that shouldn't exist is, at its heart, a story about how far human vision can reach. Across a universe 93 billion light-years wide, we're trying to study what, by definition, cannot be seen. Yet somehow, we do. Every image, every spectrum, every flicker of light is a whisper from the cosmos. Evidence gathered by instruments built to look deeper into the darkness than ever before. The James Webb Space Telescope, humanity's most powerful eye on the universe, sees light that has traveled for nearly 14 billion years. Its instruments work in infrared, detecting heat rather than visible light, the only way to see through cosmic dust and into the earliest moments after the Big Bang. With Webb, we've glimpsed galaxies forming just 300 million years after creation. We've seen black holes that should not yet exist, engines of gravity blazing in a universe still young. Each image Webb sends back reshapes our understanding of how the first cosmic structures came to be. But Webb is not alone. It stands on the shoulders of giants. The Hubble Space Telescope opened our eyes to the scale of the cosmos. Before Hubble, we could only guess how vast and filled with galaxies the universe truly was. After it, we could see them, billions of them stretching endlessly across space. Hubble captured the first clues of black holes in the centers of galaxies. It watched stars whirl around invisible points, moving too fast to be explained by anything but immense, unseen gravity. For the first time, we could measure the heartbeat of a galaxy and know there was a monster pulsing at its core. Now, Webb carries that mission forward, not just seeing galaxies as they are, but as they were. It lets us look back in time to witness the universe building itself from the inside out. While Webb peers across time, another instrument stares directly into the abyss. The Event Horizon Telescope, a global network of radio dishes spanning the Earth, acts as one planet-sized eye. In 2019, it captured what was once thought impossible, the first ever image of a black hole's shadow in the galaxy M87. That fiery ring, a glowing halo of light swirling around darkness, confirmed decades of theory. For the first time, Einstein's equations became a photograph, and in 2022 we saw it again, this time the black hole at the center of our own Milky Way, Sagittarius A. Those images weren't taken with a single snapshot. They were assembled from petabytes of data gathered across continents, synchronized to the precision of atomic clocks. It took years of computation to reveal that ring, proof that even the unseeable can be captured with human ingenuity. But black holes don't only reveal themselves through light. Sometimes they announce their presence by shaking the very fabric of reality. In 2015, detectors in Louisiana and Washington recorded a faint tremor in space-time, a ripple stretching billions of years across the cosmos. It was the sound of two black holes colliding. The signal lasted just 1/5 of a second, but it confirmed one of Einstein's boldest predictions: gravitational waves. Today, instruments like LIGO, Virgo, and CAGRA continue to listen to the universe. Every chirp they detect is the echo of a cataclysm. Black holes merging, stars collapsing, space itself ringing like a drum. With each detection, we learn more about how black holes form, how they grow, and how they shape the universe. We can also simulate the unseeable. Supercomputers recreate the birth of galaxies, the dance of black holes, and the evolution of cosmic structure across billions of years. By adjusting variables, the strength of dark energy, the rate of star formation, the mass of early black holes, scientists can compare what theory predicts to what Webb and other telescopes observe. When the simulations and observations don't match, we know we've found the edge of our understanding, the boundary where discovery begins. Behind every image of a distant galaxy, behind every gravitational wave or flicker of X-rays, are thousands of scientists, engineers, and dreamers. They operate telescopes orbiting 1 million miles from Earth. They analyze signals weaker than the hum of an atom. They turn equations into images, and images into meaning. Our ability to study black holes has evolved faster in the last 2 decades than in the previous century. And the next chapter of exploration is already being written. In the coming years, missions like LISA, a space-based gravitational wave detector, will allow us to hear the universe with unprecedented clarity, tracing the mergers of supermassive black holes across cosmic time. The Einstein telescope will probe even deeper into space-time's vibrations. And next-generation observatories like LUVOIR and HabEx will image exoplanets, galaxies, and black holes with resolution beyond our imagination. Each step brings us closer to understanding how something so impossibly dense, so perfectly hidden, could play such a fundamental role in shaping everything we see. A century ago, the idea of a black hole was just a mathematical curiosity, a strange prediction that space could fold in on itself. Today we can see them, hear them, and trace their influence across billions of light years. And still, they defy us. Every discovery about black holes forces us to rethink what we know about physics, time, and even existence itself. Perhaps that's why we keep looking, not just to answer questions, but to remember that mystery still exists in the modern universe. The black holes that shouldn't exist remind us that science is never finished. Each answer opens new questions. Each image reveals deeper shadows, and somewhere in that darkness, the universe is still writing its story, one that we are only beginning to read.